Okay, I rushed through the explanation of this problem at the end of the last screencast. Um, here's another, just a little picture that I drew to help illustrate what I was trying to say in words, right? So we have our prism here, and it's understood that this is a 45-degree angle. This is a 45-degree angle. And so when the light comes in, so we don't worry about this interface here because if it strikes the interface at a normal right angle to the surface, it will continue in the same direction. The question is what happens when it reaches this point here, going from glass to water, okay? Will it totally internal reflect or will it not? Okay, so what I was trying to explain was we draw a normal line from this point where the light hits this interface. For convenience, I'll just extend it back to this corner of the prism. And then, well, if you do the geometry right, you should be able to conclude that if this is 45 degrees, this is 45 degrees, and this is normal to the surface, this should be 45 degrees as well. In other words, the angle of incidence is 45 degrees. And it's only if this angle, the angle of incidence, exceeds the critical angle, that you will not get what you have here, which is refraction. Light actually does manage to go from the glass to the water. If this angle exceeds the critical angle, then light will completely reflect and you'll get no light refracting into the second medium. Now we've just calculated here that the critical angle for the interface between water and glass was 62.7 degrees. The incident angle, 45 degrees, definitely not greater than this. So it ends up being the case that you will get what is illustrated in this picture. Some light will get reflected out. And if you want, you can determine what that angle of refraction is. We don't worry about that for this particular problem, though. Okay, so here's another kind of interesting example using the idea of total internal reflection and what a whale is going to see. So the whale is underwater, of course. Well, I guess it doesn't have to be completely underwater, but in this case, the whale is underwater. And the whale is looking up to the surface of the water where the water meets the air. And a plane is flying overhead. What does the whale see as people in a plane as the plane flies overhead? Okay, so what is illustrated here is, well, what do we have? Here's the whale's eye, and the whale can look either directly up, or it can look at an angle over here, or it can look at an angle over here. And what is it seeing when it looks at any given angle? Well, if the whale looks up in this direction, right, following this pink line here, it is seeing a ray of light that originated when the plane was over here, and this light may have gone from the plane to the surface of the water, and then there is refraction, and in this case, the light will bend towards the normal, so you see it bending in the way that it does. And this light will reach the whale's eye, and the whale will, of course, be able to see the plane. It will look to the plane not like the plane is where it's illustrated in this figure, but more like it will look more like the plane is at an orientation defined by an extension of this line. It will appear to the whale like the plane is, well, I guess part of the plane is over here, but it will appear that this point on the plane is actually a little bit to the right. Okay, so it appears when you're looking that the light has originated from an extension of this pink line that the light follows in the water, projecting that out or extending that out into the air. Now that's not what's actually happening. The light travels along this path, bends at the interface, and then goes through the water until it reaches the whale's eye. But it will certainly appear to the whale like the plane is a little bit further to the right than it actually is. Here's another case over here. This one is more pronounced, the effect. The plane is further along, we'll call this the positive x direction. So it's moving to the right, it's further in that x direction. And the ray of light comes from the plane, hits the surface of the water, and then bends, and then the whale detects it when the light finally makes it to the eye. The whale will interpret this ray of light as though it came from, and then not along this path, but an extension of this one. It will look to the whale like the plane is actually over here and not where it really is at that moment in time, which is further to the right. Okay, so imagine the plane goes really, really far to the right, so that this light, there's some little bit of light that's emitted from the plane. Maybe it's reflected sunlight or something like that. Imagine that the plane is way over here and so far away that this ray of light is almost skimming the surface of the water. Maybe it's has to be a little bit higher than that. But this angle of incidence, if you think about it, is getting very close to 90 degrees. Okay, so here's the normal. Here's the angle of incidence between this between this incident ray and the normal. If the plane is really far to the right, then this angle between the normal and the incident ray gets closer and closer to 90 degrees. And in the limit where this plane is really, really, really far to the right, the light is basically skimming along the surface of the water, almost. But it just manages to sneak in at this point here, and it will follow this black line, right? This path traced out by this black line segment. And that is a line segment which is oriented with an angle equal to the critical angle to the normal. Okay, and you think about it, well, we're looking at light coming from air to water. Imagine the water was going from, imagine if the light was going from the water to the air. In that case, if it was following along this path, this black line, which is at an angle equal to the critical angle, and we would expect the light that initially goes along that black line would skim the surface of the water, right? That's what happens at the critical angle. Here, it's just kind of the light is going in the opposite direction. It's going from the air to the water instead of from the water into the air. So think about this. What does that imply about the way the outside world, meaning the world in the air above the water, how will that outside world look to the whale? Basically, everything that is above the surface of the water, the whale will see, but it will only be within this cone. Okay, so it's it's triangle in this figure, but you have to think in 3 dimensions. In 3 dimensions, it would be a cone. Okay, so all the light will fall between this bound and this bound in this 2-dimensional cross section of the 3-dimensional situation. That's the right word. Probably not. Okay, so think about that. All the light that is going to reach the whale's eye will, from above the surface of the water, comes in this cone here. Well, what is the whale seeing if the whale looks over here at this point on the water? Right? Well, it's not seeing anything above the water. What it's seeing is the reflection of something else, perhaps. Maybe there's a giant squid over here or whatever. And a ray of light is coming from that, reflects off the surface of the water, and that is what the whale is going to see if the whale looks outside the cone. Inside the cone, the whale sees stuff above the water. Outside the cone, over here, at all points on the surface of the water over here, or likewise on the other side, the whale is only seeing reflection of things that are inside the water, such as this squid. Okay, and so what is this half angle of the cone? Well, that's, if you do a little bit of geometry again. If this is the critical angle, theta sub c, then the half angle of the cone is also theta sub c. You can use our equation for the critical angle. It's equal to the ratio of the indices of refraction. Air goes on top, water on the bottom, so it's 1 over 1.333. Critical angle of 48.6 degrees. Okay, so that defines the angular span of this cone, within which the whale is seeing everything above the water. Outside that cone, for angles greater than 48.6 degrees, the whale is only seeing reflections on the surface of the water, okay, from below. And I think that that's what this picture down here is, that I got from the textbook with the shark looking up, and there's the surface of the water, and, well, I think that picture is supposed to refer to this situation. Okay. Question, will the plane always be visible to the whale? Well, the answer is yes. Okay, it doesn't mean that the plane has to be literally within this angle itself, right? That's not a restriction on the position of the plane. The plane can be, as we said, way over here, and then the light will hit the surface of the water and then bend down and meet the whale's eye. So the plane, no matter how far it is to the right or to the left, the plane will always be visible. Okay, and as we said, what does the whale see for angles greater than the critical angle? Just reflected light from below the water, such as the reflected image of another underwater object. Okay. Total internal reflection. Here's an application technology that you may have heard of, optical fibers, and optical fibers carry optical signals. The optical signals are just signals which are somehow encoded in light, and the light travels along these very tiny little optical fibers. And, well, why does the light bend as the fiber bends? Because you can twist and bend these fibers and the light will still follow the path traced out by the fiber. Why does the light do that? Well, because of total internal reflection. The light just keeps bouncing off the sides of the fiber, and the angles are big enough so that the light is always totally internally reflected. So it will guide the light through these multiple internal reflections. It will guide the light along the path traced out by the optical fiber. Another interesting application of total internal reflection is the mirage, which you have all seen, I'm sure, at some point. Okay, so what is a mirage? Well, if you're standing over here on a hot day, here's the ground. On a hot day, the air very close to the ground is going to be very hot. And when air is hot, well, it means the index of refraction will be lower than the index of refraction for the air when it's a little bit higher up, where the air is cooler. So you have hot air close to the road. Maybe this is a hot road in the hot summer sun. Down here, the air is very hot close to it. You have a lower index of refraction. A little bit higher up, you have a somewhat cooler air, and you have a higher index of refraction. And this change in the index of refraction as you go vertically through the air will have an effect on the pathway traced out by the light.